input data from the real world. The form of this data is a vector, and the input vector is I, and it is a series of measurements, I1, I2, I3, for as many dimensions as the data requires. These inputs are weighted by a multiplier, which gives a weight vector W. W1 is the weight for the first element, I1, W2 for I2, and so on. We sum those to get the scalar or inner product of W and I, and then we apply a threshold, and the output is S. Now, calculating this W dot I, if we're in 2 dimensions, which is very low, we can get the modulus of W, the modulus of I, and cos theta. So that equation is for 2D. But for multidimensional space, and we will always be operating in greater than 2 dimensions, we can do exactly what the model does, sum the weight of the inputs. So what comes out here is the scalar product. It is calculated by the summation over all dimensions of Wi, II. Now, training is a way of obtaining the weight vector for a problem. Whoops, get rid of that. And we use a principle called Hebbian learning, which simply means we change the weights to reduce the error. If an error occurs, change the W's. If the new W's make the error bigger or worse, ignore them. If the change in the weights makes the scalar product or the error smaller or hopefully corrected, then we take the new values. And the algorithm I gave you was a learning algorithm called error correcting feedback. Choose a random weight to get started with. So initially a random weight. Usually the 0 vector. It doesn't have to be that, but that's an obvious starting point. Having decided for a 2-class problem, whether we have class positive and class negative for the 2 classes. These are arbitrary. It doesn't have to be that way round. The first class could be negative, the other could be positive. The important thing is there are 2 decisions. Right, calculate for the first positive pattern the scalar product of the random weight vector with I, and that will give you the output S, the scalar product of Wi. If no error, it means that I is the positive class and the scalar product is positive. That would be correct. Or if the I pattern, the input pattern, is a negative class and the output from the neuron is negative, that is also correct. So if that's the case, there's no change in W. If an error, and an error is going to be where the input pattern is the positive class and S, the output, is negative, or conversely, the scalar product is a negative response and the negative class and the scalar product is positive, these will be errors. And we need to change the weight vector. And the algorithm we use to change the weight vector is to change it by adding a fraction of the input pattern. And the condition of that is the new weight vector, the updated weight vector, gives a scalar product which is equal but opposite in sign to the original weight vector. So if we get a response from a positive pattern that gives minus S, we change the weight vector, so W prime will be minus S, which will give us plus S, and it will move the pattern into the positive region. Now, to work out what C is, we substitute in this equation first for W prime. W prime is W plus C dot I, which is this line here. That goes into the equation there, and it is multiplied with vector I. And we want the output to be equal, but of the opposite sign to the original calculation. Substituting in this equation first of all, multiplying this out, this bracketed term is going to be w dot I plus c I dot I equals minus s. But we know this was the original error, and that was equal to s. So we can now substitute s for this term, and taking s over the other side, we get c I dot I equals minus s, and taking the plus s from the left-hand side to the right-hand side gives us minus 2s. And rearranging this equation, this is the correction factor. Now, if you were using a single neuron to try and solve a problem, you would obviously use a computer and you would use this correction factor, and it converges if there is a solution. If there is a solution, it will converge quicker. However, thinking of exams, that without a computer would be a correction factor, which would be a fraction. It would give some very complex fractional numbers and would be difficult to implement by pencil and paper. So if you were asked to explain how the training works in an exam condition, then instead of using this, I've given you a simpler approximation method, which is the same update factor, but instead of having a variable c, we are letting the correction factor be plus or minus 1. And we decide if it's plus or minus 1 if I is positive and s is negative, c is plus 1. In other words, if we get a negative response from a neuron, we've got to add something positive to it if it should be a positive response. And the negative condition is the opposite. If I belongs to the negative class and we're getting a positive response, we subtract. C is minus 1. So now we're having correction factors which are plus or minus 1 instead of the fractions we would get from the other method. And I started on an example. And the example was a 2-class pattern classifier. These are the 4-bit patterns. I assigned this as the positive class, and I assigned this to be the negative class. And I started off with a weight vector which was all zeros. Now, the training. The patterns are scanned and they become 4-bit binary vectors. It's not a binary number, it's a 4-bit binary vector. This is the class, the information given from above. And for the first pattern, we calculate w dot I. And if w is 0, the scalar product of that with the first pattern is going to be 0. It should be a positive class. It is therefore incorrect. So we want it to be positive. C is plus 1. And the thing to note on this table is that what is going on here in this column is a vector multiply. And what is going on the update is a vector add. And last week I got confused and I made a mistake, but the first iteration from last week's notes was correct. So C is plus 1. I add the current input pattern to the current weight vector, which is this or 0 weight vector plus this pattern. In fact, this pattern now becomes the updated weight vector. I now use the latest weight vector for the second pattern, and I do a multiply, vector multiply, which is the summation of wi, ii. It is 1 times 1 plus 0 times 1 is a running total of 1, plus 1 times 0 is still a running total of 1, plus 1 times 1 is 2. And we get plus 2. It's a positive class. It is correct. No change to the weight vector. Now we take the first negative pattern, and it is going to be the scalar of the latest weight vector, which is this one here, with the I3 pattern. And it is going to be W1 times I1. 1 times 1 is 1, plus 1 times 1 is 1. Right, yes, 1 times 1 is 1, plus 1 times 1 is 1, plus 0 times 1 is 0, and 1 times 0 is 0. It is plus 2. It is wrong. It's a negative pattern. We're getting a positive response. C becomes minus 1. And I now subtract I3 from the latest weight vector, which will give me 1 minus 1 is 0. 1 minus 1 is 0, 0 minus 1 is minus 1, and 1 minus 0 is plus 1. And that is the latest updated vector. Right. Final negative pattern, the scalar product of the latest vector with I4 is going to be 0 times 1 is 0, plus 0 times 0 is 0, minus 1 times 1 is minus 1, and 0, go away, 0 times plus 1 is 0. Total is minus 1. It is correct, no change. And that is the end of the first iteration. Now, we've been through the training set. We've ended up with a weight vector. But now I can reveal a big problem with this training method. We have changed the weight vector during training. It's got the last pattern correct, but because the weight vector has changed from the beginning, there is no guarantee that the earlier patterns will still be correct. Because in changing the weight vector, you're moving the weight vector in 2 dimensions, there is your decision surface. And this is W going out there. If I move W in that direction, then if I have a pattern here, which is the negative class, if I change the weight vector to that position, the decision surface will move, and for this original position, I'm getting 1 decision. For the updated version, I'm getting another decision, and errors could be introduced. So we have to go back over the training set. Right. Second iteration. Let's start off with the training patterns, the I's. 1, 1, 0, 1. 0, 1.
John, may I ask you something?
1, 1, yes.
We got confused on the last weight. When you did the vector add, why the last one is plus 1?
It's minus 1. That's the latest weight vector.
No. I mean for the latest weight vector. For the last weight vector, it's not minus 1, plus 1.
Yes.
How did we get that plus 1?
Right. We changed the weight. Oh, go away. We changed the weight vector after I2. Yes. No, I3.
Yes.
Yes. So we have the weight vector there. We now apply this weight vector to the I4 pattern, which is a negative pattern. It is going to be 0 times 1 times 0 is 0, plus 0 times 0 is 0, plus 1 times -1 is -1, times 0 plus 0 times 1 is 0. The total is -1, yes? And it is correct because it is a negative class.
No, I didn't mean that. I mean for the above line, from the line above.
This one here?
For I3, yeah.
Right.
If you please could do the entire line again.
Sure. Let's pick it up from I2. You're happy with the change of the first pattern. That's obvious. You're just adding the weight vector to the zero, the input pattern to the zero, right. Testing it on the second pattern, it is going to be 1 times 1 plus 0 times 1 plus 0 times 1 plus 1 times 1. It is +2. Yes?
Yes.
It is correct.
Mm-hmm.
Yes.
So we don't need to change that.
We don't change it.
Yes.
So for the third pattern, we're using the weight vector here and this pattern here. Mm-hmm. It is going to be 1 times 1 plus 1 times 1
yes.
plus 1 times 0 plus 0 times 1. It is +2. Yes?
Yes,
it
perfect.
Is wrong.
And then we have to
negative class.
Yes.
C,
and then we have to subtract 1.
C becomes -1.
Mm-hmm.
So we now subtract. It's a vector subtraction. Mm-hmm. We subtract this pattern from the weight vector. So it will be 1 minus 1 is 0.
Mm-hmm.
1 minus 1 is 0.
Yes.
0 minus 1 is -1.
Okay.
1 minus 0 is +1.
Why is 1 minus 0 and not 1 minus 1? So it becomes 0. Not.
0 minus 1 equals -1. 1 minus 0 equals +1.
Where did that not came from? That's my question.
0, third element of the weight vector, W3 minus I3. 0, let's change the color. 0 there, -1 there. 0
yes.
minus 1 equals -1. For the fourth element, 1 minus 0 is +1.
Oh, yeah.
Got it?
Got it. I thought we were subtracting -1 from the the latest vector.
-1 is the correction factor. Go back.
Okay. Got it.
There's the update. Oops. Right.
Thank you, John. Thank you.
Okay. C is the correction factor of the subtraction.
Okay.
Right.
Thank you. Thank you.
Fine. Now, errors might have been introduced, so we have to repeat the training, and the inputs are going to be 1. Oh, don't. 1 0 1 1 1 1 1 0 and 1 0 1 0. The class, same as before, is going to be, oh, what's doing with that? The class is going to be plus, plus, minus, minus as before. The scalar product W dot I, we've got to work out. We need whether it's correct or not. We need the value of C, and we need the value of the updated weight vector. And we're coming in with the weight vector at the start of the second iteration was W equals 0, 0, minus 1, plus 1. Right, the scalar product of the latest weight vector with the current pattern is going to be 0, 0, 0, plus 1. It is correct. No change in the weight vector, no correction factor needed. For the second pattern, 0, 0, minus 1, plus 1. It is going to be 0. It is incorrect because we want it to be positive. The correction factor, therefore, is going to be plus 1. We now add the current input to the latest weight vector, which is going to give me a weight vector. Let's draw the lines down here so we don't get confused. It is going to be 0 plus 1 is going to be 1. 0 plus 0 is going to be 0. Minus 1 plus 1 is going to be 0. And finally, 1 plus 1 is 2. And that's our latest weight vector. Right. Third pattern, a negative class. Scalar product is going to be 1, 0, 0, 0. It's going to be plus 1. It is wrong. We need a negative response. C is therefore minus 1. Subtract the current pattern from the latest weight vector, which will give me 0, minus 1, minus 1, 2. And so that is the latest weight vector. Try it on for the final pattern. The scalar is going to be 0, 0, minus 1, 0, minus 1. It is correct. No change, latest weight vector. That concludes the second iteration. Now, the second iteration, there has been a change in the weight vector. So although we've come out at the end of the iteration with a correct answer, we may have introduced errors in the earlier patterns. So we now need a third iteration. And the third iteration, let's write the patterns down. 1, 1, 0, 1. 1, 0, 1, 1. 1, 1, 1, 0. And 1, 0, 1, 0. The class is going to be the same as before, plus, plus, minus, minus. The scalar product, w dot I. We want the correct, is it correct? We want the value of C. Oops, not minus C. And we want the updated weight vector. And we're now coming into this third iteration with a weight vector, which was this one here. So it was 0, minus 1, minus 1, 2. So let's just note that 0, minus 1, minus 1, 2. Right, first scalar. 0, minus 1, 0, plus 2. Minus 1 plus 2 plus 1. Correct. Second pattern. 0, 0, 0, plus 2. Correct. Third pattern. 0, minus 1. Minus 1 is minus 2. And 0, minus 2. Correct. Fourth pattern. 0, 0, minus 1, 0, minus 1. Correct. No changes. So the final weight vector is 0, minus 1, minus 1, 2. No changes in the iteration, so it is getting all the training patterns correct. Now,
Sir, with I2, would the WI not be +1 instead of +2?
for I2, let's check again. 0, 0, -1, +2. It is +1. Well done. Oh, rubber come up. Right. Now, a problem. A lot of people might, oh, don't go away. Oh. At this point, a lot of people might think we have solved the problem. We haven't. We have only solved the problem for the training set. So, when you're reading research papers and you're seeing great claims for a neural network or even a neuron solving a problem, make sure that it is tested on data which is outside the training set, because to recognize the training set is simple. We can do that simply by memory, storing the patterns and their class. So, having got the weight vector, let's now use it. And to start off with, let's have an unknown pattern. A pattern which is not in the training set. And let's take a pattern which is that, the diagonal line. Now let's go back and see if I can find the original training set. Yes, there it is. For those patterns, if I compare that with the test pattern, is it a positive class pattern or is it a negative pattern? Use your human judgment. Can I have some suggestions as to whether it's plus or minus? Positive. Any other suggestions? Anybody say negative? Right, we'll go for positive. Well, that would be the human classification. What does the neuron say? So we are getting the scalar product of W dot I. The weight vector is going to be 0, -1, -1, 2. Dot. Scaling this, scanning from the top left, is going to be 1, 0, 0, 1. 1, 0, 0, 1. And the scalar is going to be 0 times 1 is 0, -1 times 0 is 0, -1 times 0 is 0, 2 plus times 1 is +2. It's a positive class. So the neuron says that pattern is positive. Now, having got the weight vector, the testing is very simple. It's just a single pass operation, a single scalar and applying a threshold. So, in practice, the training is the time-consuming operation. In real problems, if you have dimensionality of 100 and maybe 50 training patterns, there will be many thousands or 10,000s of iterations. And the problem with training is the error may get smaller and smaller it might not converge to a solution. Then you have the problem, have I done enough training, or is it impossible for that single neuron to solve the problem? That's a dilemma. But if one can find the weight vector, the testing is very simple. Now, as an exercise, take all the patterns on a 4x4 array. The universe of patterns is going to be how many? How many patterns can I display on a 4-bit binary array? It's going back to level 1 digital logic.
16.
16, thank you. Somebody remembered it. So there are 16 patterns. The training set is 4. I've tested it on a 5th pattern. There's therefore going to be another 12 patterns. Of which that is 1. So U classify the 11 remaining patterns. And because this is a very simple problem, it's only 4 bits, you might find some patterns are on the decision surface and can't be classified. That is, they give a response of 0. Now, what else can we say about this weight vector? Is the weight vector doing something useful? Does it make sense what's happened? That was the weight vector we ended up with. Now we're weighting the 2nd, the 3rd and the 4th elements, but the weight for the 1st element is 0. It effectively means the 1st element of the vector is disconnected. Now let's go back to the test set, or the training set. Here it is. And the 1st element is the top left-hand pixel. It is 1, 1, 1, 1. It is always 1. So looking at that top pixel, you cannot differentiate whether it's a positive or a negative class. So it is sensible for that weight to disappear and effectively disconnect that top pixel. All the other pixels are giving some difference in classification, a 1 and a 0, a 1 and a 0. 0, 1, 1, 0. There is in some cases, for example, this pattern is a 0, this is a 1. There's something different between the two. This one, 1, that one, 0. All the other pixels have some degree of difference. The top left hand does not. It is constantly 1. So it's reasonable that we can disconnect that pixel. It's not giving us any useful information. The second thing is it behaving like a distance classifier? Now you should, if you remember and understood the distance classifier, be able on inspection to tell me the distance between this pattern and each of the training patterns, and which is the closer. Well, remember the Euclidean distance for binary patterns reduces to the summation of the modulus of the difference of the elements. It is effectively a count of the different pixels. So looking at the distance between I1 and the test pattern, the same. 1 difference, the same. So the distance from that is 1. The distance from the second pattern is also going to be, no, it's going to be 2. 1, no, no. It's 1 again. The distance between the test and the third pattern is going to be no, 1, 2, 3. So that's the plus class. And the distance between the test and I4 is going to be 0, 0, 1, 2. So overall, this pattern is a distance of 1 from the plus class, but it is between 2 and 3 from the negative class. So it is also agreeing with the decision you would get with a distance classifier. But of course, when we come to the calculation and the classification, it is so much easier. Having got the weight vector, it is one simple scalar product to get the decision. So that is a very simple example in 4 dimensions of how a training algorithm might work. Right. Now, exams. The training algorithm is a procedure. You could make a mistake. I made a mistake last week in updating the weight vector. If a problem like this occurred in the exam and you were asked to explain and give an example of a fixed increment training algorithm, then I would always put in the exam question a limit on the iterations you do. And if you look at past papers, you've been told to do 3 iterations of a training algorithm. Now, the reason for that is if you did make a mistake and didn't have a limit on the iterations, it could go on and on and on, and you could spend the whole morning, let alone the exam period, trying to converge to a solution. So what I would be looking for in an exam is an understanding of how the update takes place. And if you were to make a single mistake in the vector addition or the vector multiplication, then okay, you might lose 1 mark, but you would still get maximum marks or near maximum first class marks for the question. So in an exam, it's the way you do the method that's important, not necessarily the answer. Right. How are we doing for time? Gosh, time is nearly over. Let's move on to problems, limitations. Of a single neuron. And let's take a well-behaved problem. I've gone down to 2 dimensions, so it's even simpler than the training algorithm, which was 4 dimensions. If I have dimension 1, if I have a cluster of patterns there, A, and I have a cluster of patterns B, these are vector points. In 2 dimensions, by inspection, you can see that will be solved by a single neuron, because a decision surface must go through the origin, and it would be defined by a weight vector. Again, it's not unique, but the weight vector would be at right angles to the decision surface. So that's the weight vector, that's the decision surface. And this would be the positive class, and this would be the negative class. You could also use the mod W, mod A, cos theta argument to get the positive and negative decisions. So it would work for that. Whoops, that's rather bad writing of the word. Theory B. Go away. What about this? (2D) dimension 1. A cluster there, A. A cluster here, B. Perfectly linearly separable, easily solved by a distance classifier. But if I have a decision surface, if I have a decision surface which goes through the origin defined by a weight vector there. I can move W in 2 dimensions. The decision surface will move, but there is no possibility that I will have all the reds on one side and all the blacks on the other side. That problem couldn't be solved by the model as it is now. The solution is simple. Bias. And the bias is an extension to the model. Our original neuron model in 2 dimensions was I1 and let's get rid of that. Machine is slow this morning. I1 and I2. Here is your weights, W1 and W2. They go into a summer. You've seen this model before, and the threshold. Introduce a third input. It will have a third weight associated with it, which will be W3, but the input to that weight is internal and it is a constant. Oh, can't spell constant. And it's usually 1. Now, what we've got now is an input vector, which in this case is 2 dimensions. There is my vector, but the weight vector is 3 dimensions, 1, 2, and 3. And in terms of the input patterns, if I include this input as this constant as an input I3, it will always be 1 for every pattern. So this is when drawing skills are testing me. What we will now have is a 3-dimensional space. I'll try and draw this as carefully as I can. That is going to be dimension 1. This is going to be dimension 2. And the problem we want to solve is a problem that looks like that with A and B. But we are adding an extra constant, an extra dimension to each of the input patterns. So there will be a third dimension, which will be 1. And this will now be the origin of the neuron. So the pattern origin is on the front face. All the patterns will be on the front face, but the weight vector will be operating in 3-dimensional space. And it's the weight vector that can move around into the board, out of the board, left and right, and up and down. That will now, in 3 dimensions, define a surface. This is where my drawing becomes a little bit tricky. Which comes out from the back area, and it will cut this front face at that point and then come out over the top. So what we've got is a surface which is in 3 dimensions. Come back. And as the weight vector rotates, the plane in 3-dimensional space rotates, and it will cut the front face at any angle depending on the position of W. It is not constrained to the origin. So as far as the pattern data is concerned, we will have two clusters like that, A and B. And the decision surface is the plane coming from behind the box, cutting at an angle and giving me a line in there. And we can assign that as the plus case and the minus case, or the other way around. So here we are introducing a third dimension, which enables the decision surface in the pattern dimensions, which is 2 in this case, not to have to go through the origin. So we have a flexible decision surface now for problems which are perfectly linear separable but don't pass through the origin. So always add a dimension. So I is equal to I1 to IN. The extra dimension can be regarded as a IN plus 1 element of the pattern vector, but IN plus 1 is equal to 1 fixed or another constant. The key thing is the patterns, if you regard them as D plus 1 space, the patterns will always have the final dimension as 1. And the weight vector will be W1 right the way through to Wn. And we will have a real weight vector Wn plus 1, and it should be. Oh, come on. And that is a real weight.
Yeah.
So, just to give you an example, it also enables us to keep still. It also enables us to classify patterns at the origin. That would be pattern 0, 0. If I wanted to classify that as a B pattern, the augmented pattern would be 0, 0, 1, where this is the pattern data. Oh, go away. That is the pattern data. This is the bias input. And if you wanted that input pattern at the origin 0, 0 to be classified as a positive class, then a weight vector W equals 0, 0 plus 1 would classify it, or that is if I belongs to the positive, or W equals 0, 0 minus 1 if I belongs to the negative class. So that is a way of releasing the decision surface from going through the pattern origin, and it also gives the ability to classify patterns which are actually at the origin. And if you are selling a neural network system, it's guaranteed that somebody will put nothing in. 0, 0 is a very common pattern to classify. Even with multidimensional patterns, a blank picture, which is all black, would be an obvious test pattern to put in. That will enable, the bias will enable you to classify it as a positive or a negative pattern. So that is an explanation of bias in neural networks. Right, I think I'm running out of time. It's 11:55 now, so we have covered some new material today. I want to go on next week to look at linear inseparability and also the number of training patterns we need for reliable performance. But in the meantime, go through that fixed increment training procedure, test on all the 16 patterns for the 4-pixel problem, and make sure you understand the update. And the key thing on the update is the testing is the scalar product multiplication, and the weight update is the scalar addition or subtraction of C's minus 1. Okay, any questions from anybody? Silence.
I think it's all good.
Okay, in that case, same time next week, folks. Have a good week.
Thank you. You too.
You too. Bye.
Cheers.